Okay, moving on to inequalities. This should be the easiest section we've covered so far. We won't spend much time on it. 1.8, inequalities. So here we'll be looking at solving linear inequalities, solving non-linear inequalities, absolute value inequalities, and then a little modeling with inequalities. So, inequalities, right? So often have to describe the solution in terms of a graph, a picture that describes all the solutions, and it's typically a segment of the number line that will solve these, that will represent the solution set. So to solve inequalities, we get to work with the inequality in the same way that we would solve an equation. We just have to observe some additional sort of properties of inequalities, that's all. So if the equation had been 4x plus 7 equals to 19, then what we would do is subtract 7 to both sides, divide by 4, and we would arrive at an answer x equals to 3. With an equation, there's only one value that makes it exactly true. Replacing the x with a 3 makes it true. When we have the inequality, well, we do the same thing, subtract 7, divide by 4, and we arrive at the statement that x must be less than or equal to 3. And so here, this graph right here describes all possible answers, right? Anything in this segment of the number line can be replaced. The x can be replaced by any value in this segment of the number line, and we always get a true statement. Okay, so the only thing we really have to do is sort of examine what are the properties of inequalities that are a little bit different than addition. So let's look at these. So here are the properties we have to be careful of. So if we have this inequality, a is less than or equal to b, this means that is equivalent to. So if we have this, it's equivalent to this. That's what this double arrow thing is saying. So this first rule is saying that we can always add a value to both sides of the inequality and maintain the same direction of the inequality. Good. This second one is saying that we can always subtract the same value from both sides of the inequality and still maintain the inequality. Note that in both of these cases, the c is either positive or negative. It doesn't matter either way. So the inequality stays the same whenever you add or subtract any constant. That's really all we really want to get away from this. Okay? Adding or subtracting any number to both sides of the inequality maintains the inequality. Okay, on the other hand, now if we just focus with positive numbers, then if we have an inequality and we multiply both sides of the inequality by that positive number, then we maintain the inequality. Right? So the first three rules here really are exactly the same as an equation. Right? You can add or subtract to both sides of the equation. You can multiply both sides of the equation by a positive number. Let's skip this one for a second and jump to this one. Also, if wait, no, that's not what I want to do. Never mind. Okay, so let's back to number 4 then. So now, on the other hand, though, if c is negative, right, less than 0 means that the constant is negative. Well, this rule is saying that if we multiply both sides of an equality by a negative number, then the new result is going to be almost the same as before, as what we would expect, but the direction of the inequality changes. That's all. So let's do an example of that part there. So what this is saying is if we start off with something that's true, like 6 is definitely less than or equal to 8. That's definitely true. And we decide to multiply both sides by a negative number. So if we multiply the left-hand side by, say, negative 2 times 6, and then multiply the right-hand side by negative 2 times 8, then we're going to end up with negative 16. Over here, we're going to end up with negative 12. And the relationship between negative 12 and negative 16 is that negative 12 is greater than or equal to. So we had to change the direction of the inequality. If you ever get confused about which one's bigger and which is smaller, remember that we can always think about it on the number line. So on the number line, numbers get larger in this direction. Always. So we have 8, we have 9, we have 10. Numbers get larger this way. So they get smaller in this direction. So going in this direction, we get smaller. And that is also true on the other side of the 0. So we have 0, we have -1, we have -2, we have -3. So numbers get smaller in this direction, and they're larger in that direction. So if we think about it from that perspective, then as we kind of extend this out here, then -16 is going to be over here, and -12 is going to be over there. So that's why it's true that -12 is larger than -16. Another way of thinking about it is kind of debt. If this is 0 and you're into debt, then someone that is only $12 in debt is wealthier than someone that is $16 in debt, right? You're closer to being out of debt, right? The inequality symbol will always face this direction on the number line. Some people think of this as the little Pac-Man guy. The little mouth of the Pac-Man guy always faces the larger number, and on the number line, it always faces that way. Okay, the next property says that if a and b are both positive, and we have an inequality that is true, this one, then what happens when we flip it over and do 1 over a and 1 over b? And so the direction of the inequality changes. Again, let's take a look at an example that illustrates that. So for example, I definitely know that 2 is less than or equal to 4. That's absolutely true. That's kind of like this right here. But what happens when I flip them over 1? So 1/2 compared to 1/4. So now what's bigger? The 1/2 is bigger than the 1/4, right? 1/2 is 0.5 and the 1/4 is 0.25. If that makes more sense. Either way, I know that the direction of the inequality has changed. Good, so that's what happens here. It's a useful property. And if A is less than B and C is less than D, then A plus C is less than B plus D, right? So in this inequality, this one is the smaller, this one is the larger. In this inequality, this one is the smaller, this one is the larger. So this property is just saying that if we add up together the two smallest ones, right, the smaller one plus the other smaller one is less than or equal to the larger one plus the larger one. That makes sense? Good. Okay. If A is less than B and B is less than C, then A is less than C. Good. So this one is less than the B, and then it's very important in this case that this is the same value there. This A is less than B, but B is less than C, so then we can connect it and say that A must be less than or equal to C. That's what that last property is. Okay, so as long as we keep track of these properties, then these problems should be easy to work with. We do all the same operations, the same methodology that we would with an equation. We just have to keep track of these new principles involving inequalities. If we multiply, and therefore by extension divide by a negative number, we got to change the direction of the inequality. And if we flip both sides of inequality over 1, then we change the direction of the inequality. And then we can use properties 6 and 7 to kind of condense two different inequalities into one. And in some word problems, that's actually pretty useful. Okay, so let's look at some examples. Pay attention to rules 3. Okay, so it's fine. And inequality is linear if each term is constant, multiple variable. To solve inequalities, okay. So here's an example. Solve this inequality. 3x is strictly less than 9x plus 4. So we would approach this in the same manner that we would if we had the equation. 3x is equal to 9x plus 4. There's really very little difference. Right? We just have to keep track of that inequality there. So to solve this one, let's see, since it's linear, I know that all I have to do is put all the terms that have, well, you know what? Let's do it that way. Let's move this one this way, minus 9x minus 9x. That'll give me negative 6x equals to 4. and then x equals to 4 divided by -6. So x equals negative 2/3. Okay, well that's what it would be like if it was an equal sign. So now let's compare that to an inequality. 9x plus 4. We follow the same steps. Let's subtract 9x from both sides, minus 9x minus 9x. We know that adding or subtracting values to both sides of an inequality does not change the direction of the inequality. So this stays the same. 6x is less than, strictly less than, 4. And now we have to divide both sides by -6, which is equivalent to multiplying both sides by -1/6. So the rule didn't specifically say anything about division, but when we divide both sides by 6, that's the same thing as saying let's multiply both sides by -1/6. Right? This is same as saying -6x is less than 4 and saying I'm going to divide this side by -6, divide this side by -6, right? Same thing. Oops, cancel that. We end up with something involving the x. Now, the point we want to drive at, though, is that we know that we have a rule that if we multiply both sides of the inequality by a negative number, we got to change the direction of the inequality. So that gives us x is greater than -4/6. And then same thing over here before I forget to change it. That way. Good. Okay, so now x must be strictly greater than -2/3. On the number line, think about where that is. So here is 0. Let's say that this is -1. So -2/3 is going to be not quite at -1. So there's -2/3 right there. And here's +1 over here. So it's got to be greater than that. So I can describe it with an open circle or a parentheses. And greater, so on bigger values, so that way. So all of these values over here can replace the x to make it a true statement. We can take a couple of those just to guess and check, just to make sure. And an easy one to do would be the value 0. It's in there. So if this is true, I can replace the x with a 0. Replace the x with a 0. And that should give me a true statement, and it does. 0 is less than 4. Right? I can also replace it with a 1. That's a nice, easy one to check. So if I replace it with a 1, it would say that 3 is less than 9 plus 4, which is 13. So yeah, that's also true. Good. We can check to make sure that this side doesn't work. -1. Okay, if I replace it with a -1, -1, that gives me -3 is smaller than, less than, -9 plus 4. -9 plus 4 is -5, and we know that that's not true. On the number line, the -5 is on the left-hand side of -3. So someone who only owes -$3 is wealthier than someone that owes -$5. Right? So this is no longer true. That's why -1 is not part of the solution set. Good? Not true. X equals -1. Okay, any questions? No? No? Okay, so author did the exact same thing. We can also use an open circle instead of parentheses, and we can also describe the exact same set using interval notation by describing it this way. -2/3 out to +infinity. Okay, solving nonlinear inequalities. All right, well, if we end up with something a little more complicated, a nonlinear inequality, then very often what we end up with is something that can be solved by using this idea that if we have a multiplication of an of a number of items, and we just want to know if it's positive or negative, then if a product or a quotient has an even number of negative factors, then the value is going to be positive. If the product or the quotient has an odd number of negative factors, then the value is negative. Okay, so what we're going to do, the strategy is going to be to move all the terms to one side so that it equals 0. Then we're going to factor everything, rewrite it as a multiplication of polynomials. Then we need to determine when that product is going to be positive or negative by identifying all the zeros, all the places where it equals to 0. In the places where the product equals 0, it will be a defining point on the number line where it changes from positive to a negative. So we can identify all those places, and then we can either use the test and check method, test the value in each one of those little sub-intervals, or analyze it in the way that I'm about to do. Okay, so the factoring technique that is described in these guidelines works only if non-zero. Okay, so for example, let's say we wanted to solve this, right? Already I can tell that this is not going to be a linear equation because there's a 2 there, and that's going to give me a quadratic of some kind. Okay, so let's move this way. So let's set up everything so that it is 0 on one side. So I'm going to copy this over here. I get x squared is less than or equal to 5x minus 6. So I'm going to subtract 5x from this side. I'm going to add 6. Subtract 5x from this side and also add 6, right? So maintain that inequality. So this inequality will still be in place. On the right-hand side, these guys canceled and these guys cancel, so I'll have 0. I know that adding or subtracting to both sides of inequality does not change the direction of the inequality, so I'm going to have it facing the same way. So x squared minus 5x plus 6 is less than or equal to 0. Good. So because I've set it equal to 0, what this is saying is, another way of describing what this is asking you is, find the values of x that produce a negative number here. That's what we want. Right? We want them to be less than 0. Find the values of x that result, that make this equation, that make x squared minus 5x plus 6 negative. Right? That's what this statement is asking. What values of x produce a negative number? Okay, so to do that, we're going to factor it. Now, that's this technique, and of course that depends on us being able to factor, so that's a whole nother problem, but okay, let's factor it. Here, it should be okay. We want two numbers that multiply to 6 and add to negative 5. So that should be x minus 3, x minus 2 is less than or equal to 0 after we factor it. That's true, okay. And if we wanted to figure out when it equals exactly 0, x minus 3, x minus 2 equals 0, right? That's one case, one thing we might be interested in. Now we can use the zero product property and separate this. This means that either this is 0 or this is 0, which means x equals to 3 is one solution and x equals to 2 is another solution. That's important to get, but it was really easy in this case, so we probably didn't need to do all that work. We can easily tell that if we let x equal to 3, then the whole thing will be 0. If we let x equal to 2, then the whole thing will be 0. And of course, because these two are equal to each other, that means that coming back up here, if I let x in here equal to 3, I replace that by a 3, replace that by a 3, I'm going to get a 0. Right? 9 minus 15 plus 6 equals 0. That's true. And at the same time, if we replace it by a 2, 2 squared minus 5 times 2 plus 6, that's going to be 4 minus 10 plus 6. That's also going to give you a 0. Okay, so we found the zeros of this, but that's not what they wanted. They wanted me to figure out when is this negative. Okay, so this is how I would recommend to do it. So I would do it. What we're going to do is we're going to come up with a number line that works for each one of the terms. Now there's 2 terms. If there was a more complicated case where you had 3 terms or 4 terms, then you're going to need more number lines. But here we only have 2, so let's do one for x minus 3. We're going to need another number line for x minus 2. And then finally, we're going to need another number line for the multiplication of the 2. X minus 3, x minus 2. Okay? All right, now we need to, these number lines are stacked right on top of each other. So the 0 is there, the 0 is there, the 0 is there. And then this is 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4. Maybe on the other side, negative 1, negative 1, negative 1. 1, 1, 2, 3, 4. Negative 1, 1, 2, 3, 4. Negative 1, 1, 2, 3, 4. Okay, so now for the first one, I want to find the 0. When I input a value of positive 3, this little multiplication becomes 0. Okay. And now, just focusing on this part, when I input a value bigger than 3, like a 4, a 5, or a 6, this little binomial here becomes positive. Right? You just simply test one value. 4 minus 3 is positive. So they're positive numbers in this direction. And by the same token, they're negative in this direction. If I let x equal to 2, 2 minus 3 is a negative. And that's going to be true over here. Okay, the place where we get a 0 is always the borderline between all the positives and all the negatives. Good. Okay, now we focus on this one. For this one, the 0 happens at 2. Here is my 0. And same thing in this direction. So as I put in values to the right of it, 3 minus 2 is positive, 4 minus 2 is positive. So they're always going to be positive in this direction. And therefore, they're always going to be negative in this direction. Good. Okay, so now we want to focus on the multiplication of the 2. So the multiplication of the 2, if I let x equal to 2, well, this first one is 0. So 0 times anything is going to be 0. So I know that this is going to give me a 0. And by the same token, this one, by the same property, this one's also going to give me a 0. Right? Because if we let x equal to 3, then that's going to be 0. 0 times 1 is 0, so it's still 0. Okay, now what we have is our number line is broken up into 3 segments. There's the segment that goes from negative infinity out to positive 2, the segment that's trapped between 2 and 3, and the segment that goes out from 3 out to positive infinity. So we just have to think about what happens when we pick a value of x that's to the right of 3. For both binomials, we end up with a positive times a positive, so everything on this side is going to be positive. Okay. On the other side over here, we end up with a negative times a negative, right? If we pick any value of x over here, both binomials give you negatives, and negative times a negative equals a positive, so I know that all those values are going to be positive over there. And then in the middle, between the 2 and the 3, if we pick a value of x somewhere in the middle, this binomial results in a negative, this binomial results in a positive, and negative times a positive will be equal to a negative. Okay. So what we've concluded is that if x equals something over here, the product of the 2 is going to be positive. If x is a value between 2 and 3, then the product of the 2 is going to be a negative. And if x is a value to the right of 3, bigger than 3, then the product of the two binomials is going to be positive. So based on all this, we can come back and answer the question we wanted to figure out: what values of x produce a negative number? And here it is, it's these. Now, it was less than or equal to 0, so that means we include the endpoints. Good. So our solution set is let x, well, there's different ways of describing it, so let's do it in different ways. One solution set could be written this way: 2, 3, with brackets to show that we want to include the endpoints. Another way to describe it would be with a graph. With a graph, we would just draw a number line and put a 2 there, put a 3 there, and then either put a color if you can, or if you're just working with pencil, you don't have colors. I'd like to do a little squiggly thing. So a little squiggly thing like this between 2 and 3 really clarifies that it's that part of the line segment that gives us the solutions we want. And maybe you might want to include the 0 so people just kind of give them context of where we are on the number line. Or we can also use inequalities and say that x must be the values trapped between the values 2 and 3. Every value between 2 and 3. Good. Questions? We can also use set builder notation, which is similar to this. We can just say that it's going to be, and now you don't have to use, well, okay, x. The solutions are going to be x such that x is every value trapped between 2 and 3. Any questions? No? No? So I like to do the 3 number lines to organize these. You know, when they get more complicated, it's just easier to add more number lines. And you know, it's just the way I like doing it. But there are other ways to do it. You can organize the information in different ways. Another popular way to do this is simply to identify the zeros. So you do this same thing and you move everything to one side, set it equal to 0, factor it, find the new zeros. These zeros break up your number line into different segments. And then what people do is just test points. Pick something in this section, plug it in, either to your the binomials, the factored form of your polynomial, or back to the original polynomial, either way. So pick a test point and check to see whether that value is positive or negative, and then kind of reconstruct the whole thing that way. So that's the way that the author chose to do it, I think. So here's what the author did. So they factored everything, right? So moved everything to one side. So we have a 0 on one side, factored it. That creates the points on the number line. So it breaks it up into 3 segments. Everything to the left of 2, everything to the right of 3, and then the one in the middle. So then you can just pick any convenient point. What's a convenient point to the left of 2? Well, it seems to me like this is a nice convenient point. What's a convenient point definitely between 2 and 3? Well, how about 2.5? That's a nice convenient point right in the middle. And a convenient point over here, well, you could go with 4, could be a nice convenient point. Or maybe 10, just because powers of 10 are sometimes easy to work with. So pick a convenient point, test it out, and see if you get positives or negatives when you do that. Good. So they picked some test values. So they used the test value of 1 to the left of 2. They used 2.5, and then they used 4. So you just plug it into your equation and determine whether it's positive or negative for each of those sections. So that's how they created the little table here to determine when it's positive, when it's negative, and figure out the sign of each of those regions. So putting it together like this. And finally, you get to the same answer we got. Okay, so it's just a matter of organizing it in a way that makes sense to you. I will accept any way you want to do it. Whatever makes sense to you is fine with me. Are there any questions? Inequalities. Modeling real-life problems frequently leads to inequalities because we are often interested in determining when one equality is more or less than the other. Okay, so let's look at this. A carnival plans for tickets. A carnival has 2 plans for tickets. Plan A, you can pay a $5 entrance fee and then pay a quarter for each ride. Plan B, you can pay a $2 entrance fee and 50 cents for each ride. How many rides would you have to take for Plan A to be less expensive than Plan B? Okay, so clearly if we are doing very little, like let's say we only go on 2 rides, under this plan, I would have to pay 50 cents from here, right, because it's 25 cents per ride, plus my original $5 entrance fee, so I would have spent a total of $5.50. So clearly this question was written like in 1950 or something, because who goes to a carnival and spends $5.50? Anybody know what the Disneyland prices were before they closed? In the neighborhood of like $150, $200 a ticket. And then they further break it down by whether you want to go to one park or both parks. Do you want to have the freedom to go back and forth between parks? Right, those are all different prices. So yeah. Anyway, okay, so the second plan, if I'm only going to do 2 rides, if I'm thinking, man, I'm just going to go in there, I'm going to ride 2 things, and I'm going to go home. Okay, under this plan, well then, for the rides, I would pay $1 from here, 50 cents each, so $1. Plus my original $2 fee to get in. So in this case, I would only end up paying $3. So in the event that I'm only going to be doing 2 rides, clearly Plan B is better. But if I'm going to be doing a lot of rides, eventually this 50 cent per ride thing is going to get pretty expensive. So we want to set up some sort of inequality to figure out when they equal each other, and then when one plan is definitely smaller than the other plan. So this one should be fairly easy. So total cost of X number of rides should be, well, under Plan A, my total cost, Plan A, well, I went to, there was a $5 entrance fee plus 0.25 times X. That was my total cost in the Plan A. And then under Plan B, there was a $2 fee plus 0.5 times X number of rides. So this is my total cost under Plan B. And then the question was, how many rides would you have to take for Plan A to be less expensive than Plan B? So maybe that's what we're looking for. Find the values of X so that this plan is still less expensive than that one. Okay, so that's what we got to solve. That should be fairly easy. Okay, so X is the number of rides. Under Plan A, it's 5 plus 0.25X. Under Plan B, it is 2 plus 0.5X. So that's the inequality we need to solve. So 5 plus 0.25X less than or equal to 2 plus 0.50x. Okay, so let's simplify these. Luckily, they're linear equations. So let's subtract 2, subtract 2. Adding or subtracting does not change the direction of the inequality, so that'll be 3 plus 0.25x is less than or equal to 0.50x. And then let's move this over here. Minus 0.25x minus 0.25x, which gives me 3 is less than or equal to 0.25x. And then dividing both sides, we get 3 divided by 0.25 less than or equal to x. Dividing by both sides by of inequality by a positive number that again does not change the direction of the inequality. And this goes into it 12 times. Right? A quarter goes into $1 4 times, and there's 3, so that should be 12. It's less than or equal to, less than or equal to x. So x must be bigger than 12. If you ride more than 12 rides, then the plan A becomes cheaper. So going back to here, we have 5 plus 0.25x less than or equal to 2 plus 0.50x. So at 12, you're going to find that both sides are equal to each other. But when you get larger than 12, 13 rides, 14 rides, 15 rides, you'll start to see that plan A is cheaper. This inequality is true when this is true. So plan A is less. Plan A costs less when x is greater than or equal to 12. More than 12 rides. 12 or more rides. If you're going to do less than 12 rides, then this is still cheaper.